Hello. Uh, Hope you are good and you are doing well in everything, and I hope also that you are doing great. Welcome again to our today's session. Today is session 4. Uh, this is session 4, and we are still in this course, MS 8102 Engineering Mathematics 2. The same content applies to MS 8122 Advanced Calculus for Electrical Engineering and MS 8102 for Mechanical Engineering students. Today's session, session 4, as I said in the last session or in the previous session, that we are going to start the multiple integrals. So today we are going to start in discussing about multiple integrals. Multiple integrals. These multiple integrals are also known as iterated integrals. Iterated integrals. The word iterated means iterations, comes from the iterations. Iterations means you have a number of steps to do before you arrive to the final destination or the final answer. That is the meaning of iterated. So multiple integrals are known also iterated integrals because in order to reach to the final result, you need to perform several integrations. And before we go further to multiple integrals, let us have a review on integration, especially on evaluating integrations as an area. Let us have a quick review on integrations. We had a good review in integrations. We had a good review in integrations. A good lesson integrations in the previous lessons. I sent it to you through Moodle some of the quick reviews in techniques in evaluating various integrals. And also, before we go to the review on integration, let us see what are we going to go through. In multiple integrals, we are going to see how we can evaluate multiple integrals when they are in Cartesian coordinates, multiple integrals in Cartesian coordinates, multiple integrals in polar coordinates, multiple integrals in cylindrical coordinates, and also we will see the application of iterated integrals or multiple integrals. And actually, here in multiple integrals, we will normally discuss only two types of iterated integrals. The first one is double integrals. We'll discuss about double integrals. Here we'll discuss double integrals, Cartesian coordinates. Then we discuss double integrals in polar coordinates, and also in triple integrals, we discuss triple integrals in Cartesian coordinates, and in cylindrical coordinates. So all in double integrals and the triple integrals, we will see and discuss about their applications. So let us now have a quick review. let us have a quick review in integration. A quick review in integration. Quick review in integration. A review in integration. A quick review in integration. Say consider the figure below. Quick review in integration. Let us consider a figure like this one. Suppose we have this function f of x. We have this function f of x, and okay, this is y, this is x. So we need to evaluate the area under the region. This is a function f of x. We need to evaluate the area under the region. So this say under the curve f of x. So say this is region A. We don't know the exact formula for evaluating the area enclosed from x, say x equals to A to x equals to B, and under this curve f of x. We don't know, or we don't have the exact formula, but we may evaluate using integration. Now we can divide this region A into small strips. Remember, we can divide this region here into small, very, very small strips, and from those small strips, we can only pick one strip. We can only pick one strip. So this is our function f of x, and this is A, and this is B, this is x. So we can divide this into very, very small, tiny strips. Very, very small strips. Very, very small strips. So that these are very, very small strips. Very, very small strips. So then, having these very, very small strips, we can consider only one strip. We can consider only one strip. Say we deal with this strip. We can consider this strip, say this one. This is strip I. Say, let this be strip I. This strip I is very, very small. Now we wanted to find the area of one strip, then multiply to the total number of strips. So we say this strip has this length delta xi, because it is a strip. And the length, its length now. So let us say we consider this one strip, this strip. So here it is delta xi, and here this y, this length y equals to half of xi, f of xi. So we know the area is given by, the area of one strip is given by this base width times height, and the height is f of xi. So, but this is the area of one strip. So if we want to find the total area now, the total area of the region A, this region A, the total region A, so then the area of region A will be the summation from x equals to A, from here A to x equals to B. When we multiply now f of x, we multiply by delta x. But the limit here, delta x is approaching 0. The limit is delta x approaches 0. That is, delta x is very, very small, approaching to 0. So in turn, this becomes the integral from A to B of f of x with respect to x. So this is how we can evaluate the area under the region A. So now going to the iterated integral, Going to the iterated now integral, we start with double integrals. We start with double integrals. So going to iterated integrals, sorry. So going to iterated integrals, we start with double integrals. Start with double integrals. In double integrals, remember, in evaluating the area under the region, we just considered the xy plane. Now here we consider the xyz plane, the xyz plane. So say, consider the figure below in xyz plane. Consider the figure below xyz in xyz plane. So let us see how our figure will look like in xyz. Okay, so let us have this figure. Okay. Good. Yeah. Good. So good. We'll have this one. So we can have this block. Yeah. So let us study this block. This is in 3D. This is our x, this is our y, and this is our z. This is z. Right. This is z. So it has dimensions. If this is x, then this is prolonging here. We have this is x1, x2, and here we have y1, here we have y2, and we have also z. You can see if we wanted to find the volume of this block, we can just pick only one piece or one strip in 3D. We can find something here in 3D here and try to evaluate. We can have something like this here. Yeah. Something like this here. Something like this one strip, and try to evaluate the volume of this one, then find the summation. So here, this is, so call this strip, call this, as we did there, call this strip I. So the dimension here, this one, this is delta xi. And is this, no, this one is from here to here, this is delta y. This is delta y. Yeah. So this is delta y, I, and the dimension here, this is delta x, I. And the distance here, this height, equals to z. And you know, z is a function of f, or a function of x and y. So z equals to f of xc, comma, y. Now, you know, find the volume equals to the same as finding the base area times height. Base area times height. Now, what is the base area? The base area is the delta x times the delta y. So it is delta xi for the volume now, the volume for block I. The volume for block I is the delta xc times the delta yi. You multiply by the length v. So, which is f of xc I, comma, y, I. So you find the volume, which is the base area times height. Now, you can rearrange, saying f of xi, comma, yi multiplied to the base area. This is the volume of block I. So if we wanted to find now the total volume of this block, the total volume now, so we say the total volume will be given as a summation. The summation of from x equals to x1 to x2, and from y equals to y1 to y2 of what? The base area now, this is the delta x, delta y, you multiply by z, which is f of x, y. But we need to know that the limit as the delta x approaches 0, and the limit as the delta y approaches to 0. So in turn, the volume for the whole block will be equal to the integral from x1 to x2, and the integral from y1 to y2, then this delta x, delta y, f of x, y. So rearranging, we have the integral from y1 to y2, integral from x1 to x2, rearranging the function f of x, comma y, with respect to x, with respect to y. So this is how the iterated integral or the double integral can be evaluated. Simple and very simple. And something to note here that when you are evaluating this, you start with the inner operation. You start operating this one inside, then you finish with the outer one. So let us see an example on how to evaluate these double integrals. Let us see an example. It leaves the two examples. Examples. Example 1. Example 1. Example 1 says, evaluate the integral from 1 to 2 and from 2 to 4 or 6, given a function 6x y square with respect to x with respect to y. So this is the first example, and let us see how we can evaluate. So we say solution. Now we have this one, the integral from 1 to 2, from 2 to 4, of 6xy square with respect to x with respect to y. So the first thing we consider the inside, the inner integral. So we start to deal with this one. We start to deal with that one. So this one remains as it is. And while we are integrating the whole one, this one, with respect to x, y is considered to be constant. Y is considered to be constant, so we do nothing to y, but we deal with x. So the integral there becomes, if you integrate there, is 3x squared, y is constant. Now this is from 2 to 4 with respect to y. So now you know how to evaluate from the integration techniques. You know how to evaluate this one. So this is 1 to 2. Substituting there the value of, this is x. So substituting the value here is 3, 4 square y square minus 3, 2 square y square dy. So this is the integral of 1 to 2. This is 1648y square minus, this is 416, so 412. So 48 minus 12 is 36y square with respect to y. So you deal with that one. So this is 36 equals to the integral of y square with respect to y from 1 to 2. So this is 36, and this is integrating is 1/3 y cubic from 1 to 2. So it is 36. Now it is it y square? Yes, it's y square. So it is now, so we substitute, this one cancels, yes, this one cancels. So we say, yeah, 3 and 36, this is 12 here. So we have y cubic from 1 to 2. So this is 12, we multiply. So this is 2 cubic minus 1 cubic, which is 12, 8 minus 7, which is 84. So therefore we say the double integral of 1 to 2 to 2 to 4 of 6xy square with respect to x with respect to y equals to 84. This is how we can evaluate the double integral of the first example. Remember here, the very, very important point is you start evaluating, dealing with the inner part. Then after completing the procedure, you repeat the same on the remaining part. So let us see now the second example so that we can understand more. Let us see the second example. Let us see the second example. The second example says, the second example is a little bit tricky. It's a little bit tricky. Evaluate says, evaluate the integral from -5 to 4 and the integral from 0 to 3 of 2x minus 4y cubic dy dx. This is a little bit tricky. It's a little bit tricky. So we say, let us see how we can deal with this one. So we have this one. The integral from -5 to 4, the integral from 0 to 3, 2x minus 4y cubic with respect to y with respect to x. So here we are instructed, or we have been forced to follow, to start with the integrating with respect to y. So The same approach that we need to deal with this one inside integral. So if we start integrating with respect to y, then 2x is constant. Remember, 2x is constant. So now we are integrating this one inside. So 2x is constant. If it is constant, then this one is going to be 2xy minus y power 4. Okay, so this one, the whole of it are from 0 to 3 with respect to x here. See here, 2x is constant. So if it is constant and we are integrating with respect to x, that is why here it has become 2xy. And integrating here for y cubic with respect to y, we have y power 4. So now evaluating, you see here we have this 3y now. Y is 3. So you multiply here 3 times 2, so this is 6x minus y is 3, so 3 power 4 is 81. 3 power 4 is 81 with respect to x. Why? Because when y equals to 0, this is 0 and this is 0, so you just ignore the second substitution of y. If y is 0 here, it becomes 0, and this one becomes 0. So we just substitute 3 there. You have 3 here, and 2 is 6x. You have 3 here, so 3 power 4 is 81. So then, again, you keep on evaluating that one or dealing with that one from negative 5 to 4. We have 6x minus 81 with respect to x. So we integrate now again with respect to x. So we'll have 3x squared minus 81x. So this is from negative 5 to 4. All right. Now we substitute 4 where there is x. So this is 3. We start with, so this is 3. 4 squared minus 81 times 4. The whole of it minus, we substitute 5. So this is 3 negative 5 squared minus 81 times negative 5, the whole of it. So this is what? So that is 1648. So this is 16 times 3, 48, minus it is 32, 4, minus to the bracket, 25 times 3 is 75, and this is also is positive, so this is 540. This is 540 positive. So this again is negative, so we have 48 minus 324 minus 480. So the final answer here is what? The final answer is negative, negative. We see here it is, the final answer is negative 756. The negative 756. Therefore, the integral, the double integral of 403 of 2x minus 4y cubic dy dx equals to negative 756. That is all about the double integrals. That is all about double integrals. So this is how we can evaluate double integrals in Cartesian coordinate. In Cartesian coordinate, it's very simple. There is no any difficulty if you know the techniques or approaches used in finding integrations. So the same procedure is applied even to triple integrals, evaluating triple integrals in Cartesian coordinates. The same procedure. So let us see how we can do the same evaluating triple integrals, but now in Cartesian coordinates. evaluating triple integrals in Cartesian coordinates. We say evaluating triple integrals in Cartesian coordinates, the procedure, the techniques and procedures are applied in double integrals as the same applied in triple integrals. So we say in triple integrals, the same techniques used in evaluating double integrals in Cartesian coordinates is applied. So there is no difference. So let us see an example. Say evaluate the triple integral. Evaluate the triple integral from 0 to 1, and from 1 to 2, from 2 to 3 of 8x, y, z with respect to x, with respect to y, and with respect to z. So let us see this simple example on how to evaluate this one. This is the triple integral, the same technique. You start with what has been given inside here, this one. So we start with integrating this integrand 8xyz with respect to x. We find the value, then we proceed with again the same. The second iteration will be with respect to y, and the last iteration will be with respect to z. So let us see how we can deal with this one. So we have this one. From 0 to 1, and from 1 to 2. So we deal with this one from 2 to 3 of 8xy z with respect now to xc. Then later we will be with respect to y and with respect to z. So this one, so we start with integrating that with respect to x. So y and z are constant, and 8 is constant. So you can factor out outside here. It can come here, 0, 1, 1, 2. You factor out 8. It can go because it is a constant. So we integrate x here. So integrating x here, we have here a half x square y z from now this is from 2 to 3 with respect to y with respect to z. Again, you can take out a half. So here you have 4, 0 to 1, 1 to 2. This is x square y z from 2 to 3 with respect to y with respect to z. So this is 4, 0, 1. Now finding the value here, 1, 2. We substitute 3, we minus by 2. So substituting 3 here becomes 3 square, this is 9. And substituting 2 is 4 on x. So it is 9 minus 4, which is 5. So this is 5y z with respect to y with respect to z. Again, you can take out 5. So here becomes 20. The integral from 0 to 1, 1 to 2, yz dy dz. Again, you integrate here with respect to y. So integrating with respect to y, here becomes a half y square. Z is constant. Now from 1 to 2 with respect to z. So taking out again a half, so there becomes 20 from 0 is 10 now. 10 from, let us see, we'll have 10, the integral from 0 to 1, y square. Oh, sorry. Yeah. Yeah. So this is, we have here 20, the integral from 0 to 1, a half y square z from, think it is from we have 20, 0 to 1, a half y square z, 1 to 2. 20, 0, 1, a half y square. Yeah. We have this one. This equals to 20, the integral a half of y square z from this is from 0 to 1 and 1 to 2. 0 to 1, 1 to 2. 0 to 1, and here is 1 to 2 with respect to z. Yes. Okay, right. So taking a half outside, we have 10, 0 to 1. This is y square z from 1 to 2 with respect to z. So this is y 10 from 0 to 1. We have now 4 square z. We substitute here, we have 4, this is 2 square, 4z minus, if we substitute 1 minus z with respect to z. So this is 10, the integral from 0 to 1, this is 3z with respect to z. Again, this is 30, the integral of z from 0 to 1 with respect to z. So this is 30. This is a half z square from 0 to 1. Again, taking a half outside, this becomes 15 z square from 0 to 1. So this is 15. When you substitute, you just get 1 minus 0. So this is 15. Therefore, the integral now, we have this kind of integral. The integral, we say the integral from 0 to 1, from 1 to 2, and from 2 to 3 of 8xyz with respect to x, 8xyz, y, and z equals to 15. So this is how we can evaluate the triple integral. It is the same approach as used in double integrals. So this is enough for today. This is very enough for today. We have seen how to evaluate the double integrals and the triple integrals in Cartesian coordinates. We have seen how to evaluate the double integrals and the triple integrals in Cartesian coordinates. Next session, the next session will be next session 5. We will study on double integrals in polar coordinates. So we'll see what are polar coordinates. We'll discuss on what are polar coordinates. Polar coordinates, just go and study or read on polar coordinates. Just go and read in polar coordinates. This is very important. You know how polar coordinates have been originated and how we can work on polar coordinates and how we can plot polar coordinates. Then we'll now go further to double integrals in polar coordinates. So please go and read in polar coordinates. So we'll have just a quick review in polar coordinates. Then after having a quick review, we'll now see how to find or evaluate double integrals in polar coordinates. That is what will be discussed in the next session. So I won't leave you alone. So go and do more exercises. Let me give you these 3 questions. Do as an exercise and make sure that you do it well. Let them in double integral. Let us start with double integral. In double integral, these are questions. Evaluate the following. A. This integral from 0 to 1 and from -1 to -2 to -1, x squared, y squared, plus cosine pi x, plus sine pi y, dx, dy. And B, evaluate from 1 to 2 and from 0 to 1 the dx dy of 2x plus 3y. This is in double integral. And try to do this in double integral. Try to do this in triple integral now. In triple integral. Try to do this exercise. So go and solve this exercise. So in triple integral, say evaluate the following. Evaluate the following. A, we say the triple integral under the region B for x, y, z, this is x, for y, z square with respect to v, where B is the region, is the block or region, a rectangular block. This is the rectangular block. B is the rectangular block, given by 0, 1, -1 to 2, 0, 3. And dv is dx, dy, dz. dv simply is dx, dy, dz. The second one, go and do this one. This is simple. This is very simple, but tricky. This is simple, but tricky. This one is tricky. This one is a little bit tricky. This is a little bit tricky. So you need to be careful here. Be careful. This says evaluate. This is a little bit tricky, but it is simple, not very difficult. Evaluate the integral under the region R, V with respect to V, where R is a region defined by R equals to X, Y, Z, such that 0 is less than or equal to X is less than or equal to 1. Again, 0. Y, about Y, 0 is less than or equal to Y, which is less than or equal to 1 minus X, and Z is 0 is less than or equal to Z, Z, which is less than or equal to 1 minus X minus Y. So this is simple but tricky. This is simple but tricky. You can do something there. Since this is dx, dy, dz, so you will start with putting inside the value of this one, then this is the middle, and the outer one is this range. So you will start evaluating. This means where you evaluate with respect to z, z equals to this one. Then you will go back inside and integrate. Here we'll need to remember the techniques of integration, integrating squares, because you will get it square. When you integrate z, you get z square, and you substitute here 1 minus x minus y, where there is z, so you square it. It's just a simple algebra. There is no difficulty. It's a little bit tricky. So I wish you all the best in doing this exercise. Please redo and do these 4 questions because they are very, very important. See you next time when we'll be discussing about double integrals, evaluating double integrals in polar coordinates. Up to a point, thank you very much and see you.